So some people sent solutions for the midterm, that's good. But I decided to give more time, so if you look on the website, the date is updated till next week. So even if you already submitted solutions but you want to fix them up, go ahead and take some more time. Okay, so last time we were talking about extensions of groups. So today I want to talk about central extensions. This is a special case, special important case. So the setting is similar to last time. So G will be a group, typically non-abelian. And if A is a G module, then we know from the theorem last time that there's a bijection between extensions of G by A up to isomorphism and the second homology of G with coefficients in A. And the way this worked, so the idea, I'm just recalling, the idea was that we chose a section of G tilde mapping to G. You choose a section of the quotient as sets. If the extension is non-split, you can't choose that to be a homomorphism, but you can look at the failure to be a homomorphism. So then so if it were homomorphism, this would be the identity. It's not typically. Nonetheless, if you apply the quotient to it, it goes to 1. It goes to 1. Therefore, it lands in the kernel, which is A. And we checked that sigma, so this is a section with S of 1 equals 1. So it's called a pointed section or base section. And you check that sigma from G cross G to A is a normalized two cocycle. Therefore, it defines a cohomology class. And you can check that. Well, it's pretty obvious that isomorphic extensions, if you match up the sections, will give the same cocycle. And then you check that different sections differ by a coboundary. So they have a well-defined cohomology class. And then you have to also construct the inverse. So the map's well-defined. This is easy to check. And we'll construct the inverse in the seminar. We didn't get to do that last time, so we'll do it today. So constructing the inverse just boils down to figuring out if I choose the section that allows me to express the group in the middle as a product, as a set. I can write everything, every element as some element in the section times some element in A uniquely. And then you check that the multiplication with respect to that product structure is completely determined by this expression. So So that's how you do the reconstruction. So we'll do that in the seminar. And today, we want to consider the special case where A is a trivial module. Special case. A is a trivial module. And then this happens then in any extension of G by A lies in the center. Because why? Because every element of an extension, G tilde, just like I said, if I chose a section, I could write this as I could look at its image in G and then take the section times A, where A is S of G inverse times G tilde. Okay? And the action of G on A, let's say G on some not necessarily this A, because it's not fixed, so on some A, by definition, by the way, by the definition of an extension, this is, for any section, it's independent of the section, this is the conjugate like this. So if that's trivial, so A being trivial, if and only if it lies in the center. It commutes with all of these, and therefore with all of these, because A commutes with A tilde. Okay, so an essential extension is just an extension by a trivial module, by definition. And essential extensions are important and also a little bit easier to classify. So there's something special about them. So this group will be easier to compute, or at least we'll have more ways of computing it. It might still be difficult. Right, okay, so let's try this. So what does trivial mean? So recall, I have the augmentation homomorphism, and this sends G to 1. So a trivial module is one that's restricted along this homomorphism. So a trivial module, this means that A is the restriction. So my notation for restriction, if I haven't used it before, is an upper star of something. I don't know, call it M. So M, just some abelian group, some Z module. That's what trivial means. It's just saying all the G's act by 1. Okay, so let's try to think about how to compute this cohomology group when A is a trivial module. I don't like this notation. So I don't know what to call it. Maybe I'll call it A bar. Okay, so let's see. To compute this, I'm going to need a certain lemma. Yeah, maybe I'll give the lemma after I show you what it's going to be useful for. So let's just try to compute this and see what happens. Okay, so to compute cohomology of G with coefficients in some trivial module, what do? We compute cohomology of, so remember cohomology is an X with the trivial module. So by definition, this is X'd I over the group ring of the trivial module Z with coefficients here. Okay. So we compute cohomology of, how do we compute this? I can take a projective resolution of the source, hom into the target, I get some complex, and I take its cohomology. So we can use standard resolution of the source So remember what the standard resolution of the trivial module looked like. We wrote it down last time. It was this bar complex. Whether we use reduced or not is not so important at the moment. So it looks like the following. There's 0 copies, 1 copy, 2 copies. So if I'm doing the reduced, I would put the quotient by 1 inside of there. And then 2 copies, and so on, with some explicit differential that we wrote down last time. It doesn't matter so much right now, just it's important that it has this form. So we can use the standard resolution of the source like this. And then we hom this standard resolution into our module. So we get a complex of the following form. So I hom this into my module. So it's hom is what it is. And so on, like that, right? Now, this is a hom, and on one side of it, here's some functor, which is restriction, from Z modules to G modules. And restriction has a left adjoint, namely induction. Okay, so I can rewrite this by adjunction. I can rewrite this as a complex, just of homs of abelian groups. And each of these will be, so this is my going to be my notation for induction. And so on. Okay? And now that's easier, because now we're not dealing with G modules, but with abelian groups. So if we understand what each of these terms are, and what the differential is, this will be some fairly simple complex. So note, remember what induction is the tensor product. So the left adjoint to the restriction applied to this module in degree n. This is the bimodule that I get, where Z is a bimodule via this homomorphism. Tensor over the group ring with the group ring. And if I don't decorate a tensor product, it means just over Z. Like this. Okay, and so what is that? If I tensor something with the ring over the ring, nothing changes. All right, so this is just, and then, so this will cancel out, and then I'll be tensoring the integers with something over the integers, so that also won't change. So as an abelian group, the total result will just be this. Okay. And so what this is, in the end, we're just taking this abelian group, A bar, and we're humming into it from the complex which computes integral homology. So let me call it star. So what is star? Star is hom over Z into the complex, tensoring with Z, over ZG, that computes homology of the group. Okay, so this is just some complex that computes homology of the group with integral coefficients, and this is some other abelian group. And now, whatever this complex is that computes homology, is some complex of abelian groups with free terms. These are the terms, right? And these are free abelian groups. Because each one individually is a free abelian group on the non-identity elements of the group. And when I tensor together a bunch of free abelian groups, I get another free abelian group. The bases, I just take the product of the bases to get a basis of the tensor product. Okay? So this is the situation we're in when we're computing X into a trivial module. We can reduce this just to humming out of the complex that computes homology with trivial coefficients into that abelian group. And now we have a general fact. You can state it more generally, but this is the case in which you need it most often. So suppose F0, F1, F2, and so on, is a complex of free abelian groups. Okay, and A bar is some other abelian group. Form the complex that you get by humming into A bar. Like this, and we need to know what its cohomology is. Then, so I'm not sure what to call this complex. Well, it's Hom dot from F dot into A. It's the Hom complex from F dot to A bar thought of as a complex in degree 0. So then there are natural in A, there are natural short exact sequences of the following form. So I have the ith cohomology of this thing, hi of this Hom complex, so this will map to Hom from hi homology, hi of the original complex F dot hommed into A bar. That will be surjective, and its kernel will be X1 from hi minus 1. Like this. So this is the claim. The Hom complex. So just like that, right? So for any two complexes, I can form a total complex of all Homs. But explicitly, it's just this. It's what you get by, the zeroth term is Hom from F0 into A bar, from F1 into A bar, and so on. And it is the Hom complex if I think of A bar as a complex concentrated in degree 0. Okay. Right. And this is split, but not naturally. So choosing a splitting is extra data. Okay. So we'll prove this, but let me say how it's relevant. So in particular, if I apply it in this situation, this here is a complex of free abelian groups because the terms are these tensor products of free abelian groups. And so this complex that computes group cohomology with coefficients in a trivial module sits in a short exact sequence like this. So in particular, we have for a group G, and a trivial, this is important, and a trivial G module we have the following. We have hi, a g with coefficients in A, sits in a short exact sequence, which is Hom, just as abelian groups, from the ith homology of G with trivial coefficients to A. And the kernel of that is x1 of abelian groups from hi minus 1 G A, like that. And this splits, but non-canonically. So I want to compute cohomology with trivial coefficients in a trivial module. I first need to just compute homology of the group, integral homology of the group, and then compute these Homs in X, and then this will be the sum of those two things, but not quite canonically. Okay. So sometimes, in nice cases, one or other of the terms will vanish, and it will just equal one of these. Okay, so this here is called the universal coefficient theorem. Or there's also a homology version. This is the cohomology version of the universal coefficient theorem. That if you want to compute cohomology with some kind of trivial coefficients, but bigger than just the integers, or different from just the integers, you need to compute homology for the integers with integral coefficients, and then compute these Homs in X. Okay, so that's what it says. So let's look at the proof. So we first need a fact which maybe we haven't mentioned before. So fact, if F is a free abelian group, and F prime is a subgroup, then F prime is free. Maybe you've seen this for finite rank groups. It's true in general for the following reasons. So to check this, you can check that X I, it's enough to check X1 into any abelian group is 0 for all A in abelian group. You can check that using the exact sequence for F prime F in the quotient. And this will imply that F prime is projective. And over a general ring, there can be lots of projective modules that aren't free. But, and this would actually even be enough at this point for our argument. But it turns out over the integers, projective is free. Because it will be surjected onto something by free, it will split, and then I have to think how to choose a basis. So maybe we make this an exercise. This will be enough for the proof. Okay, so let's take this fact, and let's look at our complex out of which we're going to take the hom, our f dot. It's a complex of free modules, that's all we know. So then consider the following short exact sequence of complexes. So I'm going to focus on degree I. There's our complex. And I'm going to look at a subcomplex of it, namely, if this is the differential, di, I'm going to look at the kernel of di, so the cycles. That's a subgroup, of course. And then the rest of it will just continue. So nothing changes out here. In this degree, I take the cycles, and then beyond that, I take zeros. Okay, so that's a subcomplex, and then I take the quotient complex. By the way, this is called the truncation. Here, I'll have fi modulo the kernel. This will be fi minus 1. Nothing will change out here because I'm quotienting by 0. Okay, but over here, I'll have all zeros. And note, I quotiented exactly by the kernel of this map. Therefore, this is injective. So that's exactly the image. This is, I could rewrite it as image di. Okay. So this is f dot. This is what's called t tau greater than or equal to I. By definition, this is what this notation of tau means, is this so-called truncation. And then I have t less than or equal to I minus 1. And the point of the notation is that you see here this has homology at most in degrees I and up. This has no homology in degree I, because this is injective. And so its homology is in degrees less than or equal to I minus 1. Okay, so I have a short exact sequence of complexes like this. And by this fact, all of these terms are free, well, at least projective. Okay. So by the fact, all the terms of these complexes are projective. In fact, free, but projective is enough. And so if I hum them into a bar, I'll get a short exact sequence of hum complexes. Because humming out of something projective is an exact functor. So this will be the source. So this will be hom from this truncation. less than or equal to I minus 1 into A bar. Then cohomology of the complex which we're trying to compute. Then Hom out of the other truncation. Okay, so that's the short exact sequence of complexes. Because what is each term? Each term of, say, this complex is Hom from one of these into A bar. And so if I want to look at what I get in each degree, it's just Hom of one of these columns into A bar. But each of the columns is a short exact sequence of projective modules. So when I Hom into it, it's exact. Okay. So there's my short exact sequence of complexes. And now I can take the long exact sequence in cohomology for this. Okay. And let's look at what happens in degree I. So now consider, so did I already call something star in this proof? I did not, so I can call this star. So consider the long exact sequence of cohomology of the short exact sequence of complexes star. What do I get in degree I? I get HI. This is what I'm trying to understand. Hom dot F dot A bar. This is going to map to HI of this. What is HI of this? Just a minute. Claim that's going to be the thing we want. Just a minute. Did I get this backwards? Yeah, no, it's right here. Okay. Okay, first let me just write down the degrees, and then we'll have to calculate something. So, I'll have, HI, 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 and then HI plus 1 of this will be what it continues on the right. What is HI plus 1 of this? HI plus 1 would appear somewhere out here where there's a 0. Right? So this will be HI of whatever this is, of this truncation. And then the next term will be some HI plus 1, which is 0, just for degree reasons, because we're Homming out of 0 in that part of the complex. Over here in the kernel, I'll also have an HI. I'll have HI of Hom of the other truncation. This is I minus 1 A bar. Okay, and here I'll have an HI minus 1 of this. But HI minus 1 would be here, which is also 0. So just for degree reasons, I get a short exact sequence like this. And so we just have to compute these outer terms and see they are what I claimed. So let's call this So let's compute this. Let's compute first that one. So we need to compute this. So we need to hum this thing into A and compute the cohomology in degree I. Okay. So we look at 0 hum kernel of di into A, then kernel, then hum fi plus 1 into A, and so on. This is what's in degree I. I need the cohomology here, so I need the kernel of this map. Okay, so I want, so this equals the kernel of this map. Okay, but that's actually easy. Just a sec, let me get that right. So for this, consider the short exact sequence. Kernel of di contains image of di plus 1. And by definition, the ith homology of the complex is the quotient. Right? So we have this. And we also have, by definition, this surjects onto the image of the differential. And then, well, whatever the kernel of the differential was. And so now, if I hum into A bar, we find this kernel that we're looking for, kernel of hom char di into A bar into, it factors through this, which injects into here. Okay, so this is what we want. And from the long exact sequence of humming into here, this is equal to hum out of hi. Bar. Okay. Similarly, let's consider X1. So likewise, we want to compute this other term. Which one was it? The one that's in the kernel. So likewise, to compute hi of hom tau less than or equal to -1 of f dot into A bar, we consider, so what are we doing? Where did it go? Oh, there it is. We hum this thing into A, right? So we consider image. Yes, okay. Do I want to consider image? Let's see if I got this right. Yes, that's image. Yes. So image of di contained in kernel of di minus 1. And the quotient by definition is the I minus first homology of f dot. So we consider this short exact sequence as well as this one. So here I have kernel and whatever the image is. Okay. And so now I want to hum this sequence into A dot. So we see the thing we're trying to compute. This is going to be co-kernel of hum fi minus 1 into A bar, mapping to hum image di into A bar. Okay, we want co-kernel of that map. And so if I take these two short exact sequences and hum A into them, I feel like I'm off by one step. No, I think that's right. Okay. So applying hum blank here into these two, so let me call them double stars maybe. I'll have hum A into here, hum A into there, hum A into there, and then some ext1 from this into A dual. This term is projective. Okay. So we'll get the following. I'll get 0 hum im di minus 1 A dot hum fi minus 1 A bar hum kernel di minus 1 A bar. Next term will be 0 because this is ext1 out of image, which is projective. Okay, so there will be a short exact sequence like this. And then at the next step, I'll have similarly hum kernel into A bar, hum image into A bar, and then the co-kernel of that map will be ext1 into the I minus first homology of f, and then the next term will be 0 because we'll be taking ext1 out of something projective. So this will be surjective. This is surjective. And so the kernel of this composite here to here to here, the co-kernel will be this. Okay. That was the claim. That's exactly what we needed to prove. Okay, so let's see. What time do we have? Okay. Very good, very good. So that's the basic calculation. And now, yeah. Did we use what? Yeah, you kind of splice so that we have some map and we're either trying to compute the kernel of the map or its co-kernel. And we break the map up into a composite of two parts, each of which appears from one of the two short exec sequences. From this one. Well, I need this term to appear somewhere, right? So I need, in one of them I need the homology group, and the other I need this Fi plus 1. Okay. Okay, so what do we do with this? We do the following. So let me give a definition. I don't know why there's a name for groups with the following condition. So the group G is called perfect. I don't know why perfect. If its abelianization is trivial. So the abelianization is always the first homology, yes? So that's always. And the condition that it be perfect is that it be 0. The first homology is 0, or the abelianization is 0. So in this case, note that the second cohomology of the group with coefficients in some trivial module, by this short exec sequence, if I apply it at I equals 2, I've already rubbed it off, this will be hom from the second integral homology of the group to the abelian group A. Okay. And this is for any trivial G module A. Okay. And we know that the left-hand side classifies extensions of G by A, but extensions of G by a trivial module are central extensions. Okay, so for a perfect group, central extensions by A are classified by this group. So this tells us, it's a little bit hard to interpret what the second homology group is. It wasn't just abelianization or something. Well, this is what its meaning is. We know what homomorphisms out of it are. And if you know all homomorphisms out of an abelian group, then you know that abelian group up to isomorphism. So this is what it does. So central extensions by A are classified by H2. And at least in the case where there might be another term which is X1 from H1 into A. So there might be more in general. But in this case, when it's perfect, there's something special you could do. You could take A equals H2. And then there's an obvious special element there, namely the identity homomorphism. Okay. So if G is perfect, set A to be H2 with integral coefficients. And then there's a special central extension. I don't know what to call it. Let me call it Xi uni. So this is Hom from H2 to H2. So this is the thing that corresponds just to the identity. There's some special element that exists in the case when G is perfect under this isomorphism, some kind of universal special thing. And why is it universal? So theorem. This is the so-called universal central extension of a perfect group. The corresponding extension central extension. So if G is perfect, then the extension associated to Xi uni is universal, is the universal central extension. In the following sense. In the sense that given any other central extension, so let's say it's looks like A G tilde G like this, with class, with cohomology class. So the cohomology class must be under this isomorphism. It must correspond to a homomorphism from H2. So I'm going to call H2 just H. I can actually construct it from the universal one. So let me tell you how. Okay. So any other central extension like this is constructed from the universal one. G uni G1 H0. So here H is this H2. Via, so what do? I take the group, the universal guy. I cross it with the group I'm trying to understand, A, and that will be too big. I'll have to take a quotient of it. It's the quotient by, let's see. So I have a map from H to G uni, just the inclusion. I also have a homomorphism from H to A. Okay, so this will be the quotient by sigma, maybe minus sigma of H. Okay, and you can check that A will inject into that in the obvious way, and the quotient will be G. So there's a universal one, and all others are built from it via this procedure. Okay, so this is not hard to prove once I've told you what the construction is. So we'll check that in the seminar. Let's see. We have a few minutes. So let's see if we maybe compute something and do some examples. In fact, we already had some central extensions in the seminar last week because we considered both trivial and non-trivial modules. When we were considering trivial modules, we were producing central extensions. But let's see. Sure, I have a good. Do I have a good example? Maybe we'll stop early and I'll cook up an example for the seminar. So the examples I would like to do, but I won't do them on the fly. I want examples of perfect groups. And describe the universal central extensions. So you know that the alternating group is simple for n greater than or equal to 5. And eventually, I think for n greater than or equal to 7, so it's simple, in particular, it's perfect because the commutators form a normal subgroup. They're non-trivial, therefore they must be the whole group. They would, being trivial would mean that the group was abelian. So in particular, it's perfect. And eventually, I think it's n greater than or equal to 7. It might be n greater than or equal to 6. H2 of the alternating group with coefficients in z turns out to be z mod 2. So the universal extension is, looks like some extension of an by Z mod 2. Okay, so we'll find a way to describe it, to compute it. Another class of examples I think are the projective special linear groups. So you can consider PSL, let's say 2FQ, and for most Q, maybe except for very small q, these are perfect. And there's a central extension just by SL2. The kernel, right, is just the units. It's the diagonal matrix like lambda 1 over lambda. That's the center. Like this. And I think this is universal. So we'll check if this is universal. So to check that, we'll want to compute the second homology group. Okay. And these are finite groups. So it turns out for finite groups, the homology will be a little easier to compute. We'll have another kind of more concrete description of it. Okay, so let's stop here. So these are some really non-trivial examples that will take us some work in the seminars.